when we talk about the work done by gravity, I throw that pen in the air. Work is the transfer of energy, right? We say on the way up, gravity is doing negative work. It's transferring energy away from the pen. So the kinetic energy of the pen, its energy of motion, is decreasing. And we know as it goes higher, it slows down. But we also have been saying that energy is conserved. It doesn't disappear. So where did the energy go? This is where we come up with the term potential energy. And what potential energy is, it's associated with the arrangement of a system of objects. So in the example of throwing the pen in the air, the system of objects is the pen and the earth. And we know that gravity wants to pull those objects together, right? So it takes a force to separate them, right? And to get this pen up high, I have to lift it, right? I have to apply that force that separates the pen and the earth to a greater distance. So the energy associated with the arrangement of a system of objects that exerts forces on one another, I have separated the pen and the earth with a greater distance now. And so that energy that I did work to do that, now where did that energy go? We call that storage of energy potential energy. And now that the pen is up here, the energy is stored. And if I want to get it back, all I have to do is let the pen fall. And now I get that potential energy back in the form of kinetic energy. Same thing with a spring. That quiz problem that we did recently, right? If I have a block and I let it fall onto the spring, as it begins to compress the spring does work on the block. It does negative work. Just like gravity was doing negative work on the pen on the way up, slowing it down. As the block compresses the spring, the force of the spring is up, the displacement of the spring is down, so they're in opposite directions. The spring does negative work, and it transfers energy away from the block. Where did the energy go? So again, now our system of objects are all the molecules of the spring. When we distort them and we bend them by pushing the spring, they want to push back. Okay? And so we call that elastic potential energy. Whereas if something is up high, we raise it to a height, we call that gravitational potential energy. Now, when we compress or stretch a spring, the work that we had to do that now is stored in the spring in the form of elastic potential energy. Okay? So I've summarized right there the two types of potential energy that we'll focus on in this chapter are gravitational PE and elastic PE. There are other forms, right? When I lifted this pen up to create gravitational potential energy, where was the energy before that? It came from me, right? I walk around and, hey, I got some energy in my pocket. You want some? No, where is it?
The money.
It's stored in my muscles, right? That's chemical potential energy, right? When we move our muscles, we're burning glucose and oxygen and all that respiration stuff, right? That's stored chemical energy. So there are other forms of potential energy, okay? Don't get me wrong. But we're going to focus on these two for this chapter, gravitational and elastic, okay? All right. So in section A2, we see that this important equation. Okay, so you might see K for kinetic energy. You might see KE for kinetic energy. You might see PE for potential energy. Or you might see U for potential energy. So U and K, I think, is what the book uses most of the time. Just because it's my habit from when I was in college, I guess. I tend to use KE and PE, but either one is fine, okay? U and K is just a little, less writing, but whatever. Okay, so what does this equation mean? Well, when the pen went up into the air, the work done by gravity was negative, and it was converting kinetic energy to potential energy. So the work was negative, but the potential energy was increasing by the same amount. And the spring When the spring did negative work, same thing. The kinetic energy was decreasing, but the potential energy was increasing by the same amount. So the sign on the work is opposite to the sign on the change in the potential energy, but they're the same amount. So we can say then that whatever work is done by the gravitational force, by the spring force, whatever, that amount of work, if you take the opposite of it, that'll be the change in the potential energy. Okay? And if you remember, the work done by the gravitational force was minus mgd. Guess what the change in potential energy is? Positive mgd. But usually we use the letter h instead of d for height. Because remember, d was the vertical displacement, right? So potential energy, and we label it with a little g, is equal to mgh. And that's what you see down there under section A3. The change in potential energy is mg times delta h, okay? So if you let the lowest point, delta h, is equal to the change in height, the final minus the initial. But if we use this as our reference point, we can say that's 0. Our 0 height, we call that the reference point. Then the delta h is just the height above that point. Okay? Likewise with the spring, remember the work done by the spring was equal to 1/2 kx initial squared minus 1/2 kx final squared. Right? So the change in potential energy is the negative of that. So delta U on the spring makes this positive and this negative, and so that's equal to 1/2 k x final squared minus x initial squared. Okay? So the change in potential is just the opposite of the work done by the force. And again, if we let the initial position be our reference point, 0, and if we're always comparing that to the relaxed length, we say that's the relaxed length. If we're always using that as our reference point, then we can say the potential energy of a spring is 1/2 kx squared, where this is the distance from the relaxed length. Okay? So that's the amount of energy stored in the spring. If I compress it, where did the energy go? Now it's stored in the spring. How much is there? 1/2 kx squared, where k is the spring constant, x is the amount of compression or stretch. Okay? Now, we have to differentiate between different kinds of forces. If I throw this pen into the air and somehow catch it up here, now that potential energy is waiting for me to use it. All I have to do is let go, and I get that energy back. And anything that's up high, if it falls, it'll get kinetic energy back. Something had to move it up there at one time. Okay? Any force where if we change it to potential energy and we can get it back, we call that a conservative force, because energy is conserved. We don't lose any energy. When we do lose energy, that would be something like friction. So if I take a book and I slide it across the tabletop and it stopped, where did the energy of motion go? Friction turned it to heat, right? I can't use that heat to make the book start moving again. Potential energy, yes, I can get the kinetic energy back. Thermal energy, if it converts to thermal energy from friction, I can't change that energy back to kinetic energy. So we differentiate between those two types of forces. If we can get it back into kinetic energy again, we call that a conservative force. The spring force is a conservative force. The gravitational force is a conservative force. But friction and air drag, whenever the energy turns to heat, we say that's a non-conservative force. And it's not that energy disappears. No, it just turns to a form that we can't use it. Okay? It turns to heat. So that's the difference between conservative forces and non-conservative forces. And you see I've made a note there. For conservative forces, 100% of the energy can be returned to KE from the PE. Okay? And when that is true, it turns out the path that an object takes from one point to another is all that matters is where it started and where it ended, for how much work is done. We call it path independent for conservative forces, because if you think about what's happening, if I go from this initial height to this final height, I know that the work I did is equal to the negative change in potential. So that's mgh, right? If it goes up, potential energy increases. Let me see, sorry, I got it wrong, right? Okay, it doesn't matter. If h goes up, my potential energy increases, and the work done on it is negative by gravity as it slows down, right? If I were to go a little higher and let it come back down to that spot, now I had a lot more negative work done by gravity, but I also had some positive work done by gravity. And so this negative amount plus this positive amount still gives me this same amount that I had if I had just moved from there to there without going up there. And in fact, I could go up and then down and up and down and up and down and up. And in the end, if I start and stop at the same place as this example, right? All that matters is my delta H. The net work will depend on that because it's a conservative force. Whatever work I do in the negative direction, I get back when I do it in the positive direction, and in the end, all that matters is the difference in H. Okay? So we call that path independent. And the same thing goes for the spring. If I move a spring from here to there, it doesn't matter if I move it out here and then back here and then here and here, and then as long as it ends up at the same final position from the initial position, the amount of work done by the spring is the same. Okay? And the change in potential energy is the same. Once we start letting some of that energy go to heat, then we can't say that anymore. Okay? That's called path independence of conservative forces. All right, let's take a look at 8.5. We've already done an example demonstrating this concept, and that was our energy of a tossed ball lab. What it's saying is the kinetic energy and the potential energy, K plus U, together is a fixed amount. And we saw that. Remember our graph of total energy for the tossed ball up here was a constant number. And that was the sum of the kinetic and the potential together, right? We give a special word for kinetic energy and potential energy due to gravity and potential energy due to the spring. Those can all be clumped into the category called mechanical energy. Okay, so K plus U, we call that E mech. That's the mechanical energy. And just like we saw in the lab with the ball, it stays the same as long as there's no outside forces coming in to your system. If we say the system in the toss ball lab was the ball and the earth, then the whole time that the ball and the earth were interacting, the total energy stayed the same. But if I reach in with my hands and lift up on the ball, now that's an external force. I'm adding energy to the system. So this total amount of energy changes because I'm adding energy to the system. Now if you include me in the system, then you say, oh, well the energy added to the ball and the earth came from Mr. Taylor's stored chemical energy in his muscles, and now the total energy is the same again if you include me as part of the system, right? Because what the ball and earth gained in energy, I lost in energy, and the total amount still stays the same. It all depends on how you define what is in your system. As long as your system is closed and there's no outside forces, this is going to be true. The total energy stays the same, but the categories into which they fall can change. The buckets, if you want to call it, is the way I like to say, where the energy is and which bucket it's in can change, but the total amount stays the same. Okay? And so if this goes up by some amount, this goes down by the same amount. So another way we can write this is to say that the change in kinetic energy plus the change in potential energy is always zero. Okay? They add up to the same amount, and the total amount of change is zero. All right? Now let's take a look at the quiz problem, how we would have solved it before and how we can solve it now. Now we have another option. Okay, so this is the quiz problem that we did recently, right? The block is falling onto the spring, and here's the way we did it before. We used the work kinetic energy theorem. It said the net work is equal to delta KE, and the net work is the work done by all the forces. So that's the spring force and the gravitational force. We know that the work done by the spring force, 1/2 kx initial squared minus 1/2 kx final squared. The work done by gravity was positive, and it was the force times the distance, which is the weight, times, I've defined that distance the spring compresses to be x sub f. Okay? And that equal to the change in kinetic energy, where the final kinetic energy is zero when it gets to the lowest point. It's not moving. So zero is the final kinetic energy. So negative spring work, positive gravitational work equals negative 1/2 mv initial squared. And that was the equation we used to solve the quiz problem. This was the answer to part A of the question. This was the answer to part B of the question. And solving the equation for V was the answer to part C of the quiz question. Very good. Now let's look at it from a slightly different vantage point. Let's look at it from the viewpoint of conservation of energy, that says the total mechanical energy, the sum of all the energies, doesn't change. The energy can change forms, kinetic energy, gravitational potential energy, spring potential energy, but the sum of them will always be the same. So that's what I've said here. The sum of all the energies at the beginning, whenever I determine that to be, equals the sum of all the energies at the end, whenever I determine that to be. So the beginning will be just before the block hits the spring, and the final will be when the spring is compressed its maximum amount. Okay? So initially, kinetic energy is 1/2 mv initial squared. 1/2 times the mass of the block times the speed. It's going just before it hits the spring squared. Now the potential energy for gravity, we have to take a moment here and decide where is our reference point going to be. Right? If I just sit on this desk, if I say the tabletop is my reference point, I have no potential energy compared to the tabletop because I'm at the same level. But if I say the floor is the reference now, if I fell off the table, I would accelerate to the floor and I would reach the floor with kinetic energy. And the potential energy that I had up here would change the kinetic energy down there. And that would be determined by mass times gravity times height. But that height is a height above a reference point. So I'm going to say right here, I'm going to use this lowest place that the spring compresses to, I'm going to use that as my reference point for gravitational potential energy. So that means just before the block hits the spring, it is this distance above my reference point. So mass times gravity times height is gravitational potential energy, where height is this distance, which is xf. Okay? So my potential energy then is mg xf at this point. And then the potential energy of the spring, it's not compressed at all. So x in the spring equation is 0. That's the amount of compression. So my potential energy of the spring at the beginning is 0. Then at my final point, that's when it's at its lowest spot, the block has stopped moving when it gets to the bottom. So there's 0 kinetic energy. There's no height above my reference point, so there's 0 gravitational potential energy. And now all the energy from before has been stored in the spring, which is 1/2 kx squared. So rewriting the equation without the zeros, I see that the kinetic energy plus the gravitational potential energy here equals the spring potential energy here. Okay? And if I go back over to the equation that I had with the work kinetic energy theorem, if I just rearrange some terms, you can see I can come up with the same equation. So the work kinetic energy theorem and the conservation of energy, they're really saying the same thing, just in a slightly different way.